Hello, it's Mr. Bush here, and today we're going to review the key components of the universe, HR diagrams, and the four seasons and rotation and revolution of our Earth. So let's go ahead and start off with the components of the universe. Well, first off, we have asteroids. They're basically just large chunks of rock. They're orbiting the sun. Most of them are found between Mars and the Earth. And the next thing, or between Mars and Jupiter, kind of out there in the asteroid belt. Comets are large balls of dust and ice. They don't produce their own light. All they do is reflect light off the sun, and they kind of form what's called an elliptical orbit. Their orbit is a lot more oval shaped than ours. Alright, stars are large balls of hydrogen and helium gas, which their pressure creates a massive nuclear reaction that goes on for several billion years. Our sun is one star, and all the light and warmth we get from it comes from this nuclear reaction. Alright, nebulas are going to be large clouds of gas. These are where stars are born. They're often called a stellar nursery because all of our stars originated out in a nebula until enough of the gases came together to create that nuclear reaction. Alright, in galaxies. Galaxies are going to be made up of millions of different stars. Our own sun is just an average sized star on the edge of a disc-shaped galaxy called the Milky Way. Let's go ahead and look at an example of each one of these. These are asteroids, as I previously mentioned. They do not produce their own light. They're just basically large chunks of rock. Some of them are anywhere from about half a mile to 20 to 30 miles across. And they just orbit around the sun. The sun's gravity is what's going to keep them in orbit. So basically the reason why they keep circling the sun is the gravity between, the gravitational pull between the two of them keep them from going off into space. Alright, let's go ahead and look at a comet real quick. Now, this is a picture of Halley's Comet. As you can see, it looks very bright, but it actually does not produce its own light. Instead, like the moon, it's reflecting light from the sun. Now, they form a very unique orbit. Instead of following a nice, small oval shape like our orbit does, they have a very elongated orbit. They go way out into space and they come very close to the sun. But once again, the sun's gravity is what's keeping them in orbit. Otherwise, they'd fly off into space and just keep going in a straight line. Alright, let's go ahead and look at a couple stars. Actually, let's look at a nebula first. These are two nebulas that were basically, the picture was taken from the Hubble telescope. That is a telescope that's up in basically it's orbiting the Earth, so since it's outside of our atmosphere, we're able to get really good pictures like these. They're large clouds of gas, and over time the gas basically forms together and eventually will form several stars. So that's why they're called a stellar nursery. This is where our stars are born. Let's go ahead and look at a couple stars. Alright, this is a picture of basically what you would see in the night sky. Basically just a couple stars out there. From our Earth, they do not look very big because they are literally billions of to trillions of miles away. Let's go ahead and look at a couple, like a familiar constellation. This is going to be Orion's belt. You often will see this part right here very clearly in our night sky right here, and that's going to be called Orion's belt. So the stars, even though they look very tiny from Earth, the reason why is they are very far away. Many of these stars that look like tiny little dots in our sky are actually much larger than our sun. However, the reason why our sun looks much larger is the sun is very close. Think of it this way: if someone had a weak flashlight about 4 or 5 inches from your eye, it would look brighter than a very powerful flashlight half a mile away. Let's go and look at some of the temperatures of our stars. Alright, stars come in different colors. Their colors are always based off their temperature. Now, as you can see, the red stars tend to be the coolest, which at first doesn't make a lot of sense until you start thinking about like fires or flames. Blue flames tend to be much hotter than red flames or a yellow flame. Now as it goes along, basically orange is slightly hotter than red, yellow is hotter than orange, white is usually going to be a very hot star, and our hottest star is going to be our blue stars. Now, stars, their brightness is always determined based off their size. So this basically brings in the question of how do we classify them? Because there are literally trillions of different stars out there. Well, they came up with a diagram that classifies stars based off their temperature and their brightness. This is our HR diagram. They come in a lot of different forms, but they're pretty much always used to measure stars based off their brightness and their temperature. Now, the bottom down here measures only temperature. Right here. Basically, it is cooler at the back end. It gets hotter towards the left end. Now, I'll go ahead and write that in. Now, the vertical column right here basically is going to measure brightness. The middle is almost always one luminosity. That's going to be one, basically the equivalent to the brightness of our sun. So our sun is right here in the middle. We're a very average brightness star. Basically, we're not very bright, we're not very hot, we're just right there in the middle. So if y'all look here, that one luminosity, that's going to be basically one brightness of our star. Now as you go up, it's going to get brighter. So anything above 1 is going to be brighter than our sun. Anything that is basically below 1 is going to be dimmer than our sun. And basically temperature and brightness are going to be independent of each other. As you can see here, this star right here has the same exact temperature as the star up here. But their brightness is different because, well, a supergiant is going to be much larger than like a red main sequence star. Alright, and this is basically, that's how you tell these apart. So if you want to know, let's say, the brightness and the temperature of this star right here, what you would do is you would go straight down. You would estimate its temperature there, so it would be about 5,000. And if you want to find its brightness, you'd go straight across, like right over here. And it would be close to about 100 times brighter than that of our sun. Let's go ahead and look at one more picture of these, and then we'll move on. Now, scientists use many different, basically, types of HR diagrams. They don't all look the same, but they do have some common features. The temperature is always basically the same at the bottom. It always goes from coolest over here, and then gets hotter as you go to the right. As you go up is always brighter. As you go down is always dimmer. And this one kind of gives you a good look at what the stars would look like. The dimmer they are, typically the smaller the star is. The brighter it is, the larger it is. And then with the colors, it goes from red to orange to yellow, and then white, and then finally blue. Think of it like if you're heating up metal. It starts off red, and then it starts glowing a yellow. And once it starts to melt, it's almost a white color. And think of like the really hot flame as being blue. Alright, let's go ahead and move on to the next topic. Alright, now day and night on Earth is caused by the rotation of the Earth. Think of the sun as a flashlight. When it shines on the Earth, one half is in light, the other half is in darkness. Now as the Earth turns, that's why basically it looks as the sun is moving, where basically one half is going to get this daylight until it rotates back around to the other side, and then it's going to have night. One day takes 24 hours. So basically, every single day on Earth is 24 hours. That's going to be one rotation. And that's pretty much all there is to it. You have to have the sun to create the daylight, and the backside or the shadow, that's going to be night. The Earth rotates around, and it takes 24 hours. Let's go ahead and look at the next one, our revolution. The 4 seasons are basically caused by the tilt of the Earth's axis. It's not the distance between the Earth and the Sun. Basically, as the Earth revolves around the Sun, so as it's going in a circle or one full year, the tilt basically causes certain parts of the Earth to be tilted towards the Sun. If you look here, during winter, the northern hemisphere is being tilted away from the Sun. That's going to make it have less direct sunlight. However, the southern hemisphere is being tilted towards the Sun. That's going to cause it to basically have summer. Now, right here, the next stage would basically be spring. And if you notice, the Sun is basically shining evenly on both sides of the Earth. Then, over here to the next section, now the northern hemisphere is tilted towards the Sun. That's going to cause it to get the most direct sunlight. And the southern hemisphere is tilted away. So, what happened would, the northern hemisphere would have summer, and the bottom half would basically have winter. Now, once you figure these out, like once you figure out where summer and winter is, you can kind of predict the next season. So if you know the top half is having summer, well, the next one after that is going to be fall. And if the bottom half had winter, then they would have their spring. As you can see, the sun is basically shining evenly on both halves, and then the cycle repeats itself. All right, let's go ahead and look at that in a little bit more detail before we're done. All right, if you look here, basically, our equator is right here down the middle. This top half is going to be the northern half, and the bottom half is going to be the southern half. Let me put that in. Northern, southern. Now, if you notice, the southern half is getting the most direct sunlight, which would make it basically have summer, while the top half is being tilted away, so it would have winter. And that's basically, I know a lot of y'all were taught it's basically the distance between the sun and the earth, but that's not true. It's all about the angle. If you look here, you always look for where's the axis being tilted. As you can see, that axis is tilted towards the sun. This one is being tilted away. And basically that's all there is to it. If the axis is tilted away, you're going to have winter. If it's tilted towards it, you're going to have summer. Let's go ahead and look at one last example before we're done. All right, if you look here, basically the equator goes right down the middle. The top half is going to be the north half. The bottom half is our southern half. And as you can see, the north half is tilted towards the sun, making it summer. And the bottom half is tilted away, making it winter. Remember on the STAR test or any homework assignment to draw your arrows. And also write your seasons out in order before you start one of these problems. That way, whenever you're counting them, you don't get confused. Because I know it seems silly, but a lot of students do. Hopefully this was helpful, and you'll have a great day.